Hello, everybody. Today, we would like to talk about Intel and Hazelcast cooperation in context of persistent memory. My name is Michal Biesek, and I'm a software engineer working in Intel. I'm a lead developer in Memkind project. My other work activities are enabling different applications, essentially databases, to work with persistent memory. The presentation is divided into parts. I will provide short introduction to Memkind library and showing what functionality this library offers. The second part, led by Zoltan, will move on the presentation of in-memory data grid solution, the integration with Memkind library, and Hazelcast performance results achieved with PMem. The main benefit of persistent memory in the volatile variant is a memory expansion, a larger capacity of persistent memory than DRAM at fraction of the cost. The simplest way to achieve this variant is to use persistent memory in memory mode, in which we don't use any libraries. DRAM is treated as an L4 cache where the memory controller controls data placement and memory cannot be explicitly managed by the operating system. If memory mode does not give all the performance user expect, which might be because user application workload is not cache friendly, we could use a different approach. In UpDirect mode, PMem and DRAM are treated as separate memory tiers. And we could look up into these memory tiers only as volatile memory heaps with different memory properties. In other words, for objects which required low latency, we could use DRAM pool, and for non-latency sensitive allocations or large size allocation, we could use PMem pool. And to achieve this goal, we could use multiple disjoint libraries to handle each memory medium individually, but we propose to have a general solution in form of one library to manage heterogeneous memories, a Memkind library. With the usage of the Memkind library, we get memory management control on the application layer. Memkind is a heap manager, a library where you have absolute control where you place data on user level software. This is done by providing an abstraction for different types of memories. Abstraction takes the form of different independent pools with varying characteristic of performance called memory kinds. Memkind library is written in C. It is thread safety, open source, and available on Linux. It is built on top of the JMalloc, which means that the memory allocation algorithms are handled by JMalloc. As you can see, Memkind API is presented as malloc-style API, well known from the standard glibc implementation, with a slight difference. The first argument is the memory heap on which we would operate. Memkind internally tracks the kind of given object from the allocation metadata. In other words, you don't have to remember from which medium you got your memory and keep extra metadata in your application. Memkind will handle detecting correct memory kind for you. This feature is presented on the slide as passing null pointer in the place of memory kind in freeing memory operation. Detecting memory kind from memory referenced by an address would be done explicitly as well by Memkind detect kind function. It is worth mentioning that using this functionality comes with performance costs related to internal search based on pointer address. The second feature available in Memkind is a heap manipulation. Even though the heap's actual logic is handled by JMalloc, Memkind provides a mechanism to manipulate a heap, later discussed during this presentation. Memkind supports persistent memory in two ways. Both ways use DAX property to establish direct mappings to persistent memory media, removing page cache from the input-output path. Here we see the comparison between the two modes. File system DAX solution, in shortcut FSDAX, is based on file allocation of the file system DAX capabilities. This solution is commonly available since it relies on kernel 4.2, available for a long time. In this approach, memory kind is a memory mapped temporary file, and the allocation are based on manipulating the allocated file space. Since the file system can be mounted on a different location, creating a new FSDAX memory kind requires additional action. This extra action takes the form of memory kind management operation. Besides pointing path where make memory kind, user can restrict the maximum size of the file-based heap, obtaining pool size control in this manner. The second operation mode is KMenDAX. Linux version 5.1 supports the volatile use of persistent memory as hot plugged memory region, functionality called KMenDAX. From the operating system perspective, PMem looks like separate memory-only NUMA node. Memkind supports detection and allocating these nodes in the memory binding call provided by the NUMA-CTL API. PMem DAX variant doesn't require memory kind management operation, since a memory kind is available as a predefined object in the Memkind interface. In contrast to file system DAX solution, Memkind library in PMem DAX provides NUMA awareness. And this will be the end of the first part of the presentation. Now we proceed to the second part of the presentation led by Zoltan.
Hello, everybody. My name is Zoltan Baranyi, and I'm a software engineer at Hazelcast. I implemented the persistent memory support for Hazelcast, and I'm going to speak about this in this presentation. The first few thoughts about Hazelcast. Hazelcast is a distributed in-memory computing platform, kind of a piece of an infrastructure software, which is typically used as a caching layer, or web session used for real-time analytics or fraud detection, or many other use cases. The main feature of Hazelcast is a key value store, but it also supports rich features like streaming, executing SQL queries on top of the stored data, and many more. As Hazelcast is mainly used as a key value store, it typically manages big in-memory state, which is tricky because Hazelcast is written in Java. And as it's widely known, the heap in Java is managed by the garbage collector, which means the garbage collector algorithm either can cope with the big heaps or can manage the big heaps at a certain cost in terms of CPU or memory overhead. So years ago, Hazelcast implemented its own solution for this problem, and it's called the high-density memory store. The high-density memory store segments the heap into two parts. It still keeps the JVM managed garbage collected heap, which hosts the temporal data structures and all the working variables that the Java code is working with, while it has a separate HD memory store, which is outside of the JVM heap, and therefore it is not subject of garbage collection, and the garbage collection poses don't scale with the data stored in this memory area. So there is no resource overhead, and in this pool, the memory is managed manually. So when the first persistent memory modules came out to the market, we thought the persistent memory is a good fit for backing this HD memory store, because higher memory density or more memory is available at a lower cost. So the persistent memory in Hazelcast is supported in the volatile at direct mode, as the Intel Optane persistent memory terminology calls it, and it's supported only on Linux. First, the Hazelcast 4.0 version came out with supporting the persistent memory via libvmem, with limited support of multi-socket machines. It was supported only via LVM, which comes with some NUMA locality problems. In Hazelcast 4.1, the libvmem library has replaced with Memkind, and now we support the multi-socket machines in a native manner with optional NUMA awareness. And we both support the FSDEX and the previously mentioned PMem DEX modes that the Memkind library supports. So during the integration with Memkind, we learned that actually the integration was easy, because internally Hazelcast, the memory allocator interface looks like it's a malloc-like interface, while the Memkind interface, public interface, is also a malloc-like interface. The challenge we needed to solve is that Memkind is a C library, while Hazelcast is operating in the Java space. So that means every single call that we make to Memkind has to go through the GNI, which is known as an expensive operation if it happens too frequently. So in order to amortize this GNI overhead cost, we use Memkind as a page allocator library, and the pages are split up inside the Java application, and the pages are thread cached for the best performance. We also don't uncommit the memory until the Hazelcast application exits. This means every Memkind-free operation happens at the shutdown phase of the application. But as Memkind-free operation typically comes with hole punching in the FSDAX mode, which is known to be a very expensive operation again, Hazelcast leverages the Memkind hung memory feature of Memkind, which means this hole punching is entirely eliminated when the Memkind free is called. So the shutdown times of Hazelcast get reused by this feature of Memkind. And apart from the persistent memory support, Hazelcast can optionally support every memory kind that Memkind supports, like huge pages, or can support the other kinds with different NUMA policies. This is an option for the future. The other challenge with the FSDAX mode is that in that mode, every socket's persistent memory is mounted as a separate mount point, which means each socket, the persistent memory, is a different Memkind kind, therefore a separate heap for the Hazelcast application. And the allocators of Hazelcast are not aware of having multiple heaps. They see the entire heap as a single heap. Therefore, we had to solve this as the allocator level, which made us to come up with allocation strategies. And the allocation strategies determine for every single allocation request to decide which heap to take for the allocation request. We implemented a round robin and the NUMA-aware allocation strategy, where the NUMA-aware allocation strategy turns every persistent memory access a NUMA local access. The second challenge in this mode was that every Memkind free call needs to free the allocated memory block from in the heap or in the Memkind kind where the block was coming from. And here the Memkind's kind detection feature that Michal mentioned previously was a great help, and we just need to call the Memkind free with null pointer, and the Memkind is doing the heavy lifting for us. So I brought some benchmarks to this presentation. This is a caching benchmark, which was executed on 3 servers, where the servers were running on dedicated machines. And the load was provided by 20 clients, and these 20 clients were sharing 2 machines. The clients and the servers were all connected with a low latency and high bandwidth 40 GB network. Each entry size in this key values or caching benchmark used 10 kilobyte entries. It's a fixed entry size, and every server hosted 100 gigabytes of primary data and 100 gigabytes of backup data, so 200 gigabytes in total. And we used persistent memory in FSDAX interleave mode. In the following charts, there will be a naming convention, which is seen on the right side. So the first part, the fNUMA, means the worker threads of Hazelcast were NUMA bound by using the thread affinity library of the Linux kernel. DRAM or Optane is whether stored on DRAM or persistent memory. And Optane NUMA means the NUMA-aware allocation policy was used, and the rest is what I already said. The first benchmark result is seen here. So the red line is the best available DRAM performance. This is our baseline, and we compare the 3 persistent memory results against it. The green line is the NUMA-aware allocation strategy. It's pretty close to the baseline. While the blue line is it comes with NUMA-bound worker threads, but by using the round-robin allocation policy. And the gray line is the round-robin allocation policy without NUMA binding the worker threads. So we see that there is a separation between the performance, and the best is the NUMA-aware case. As we increase the load, we see that the NUMA-aware allocation policy is still close to the best available DRAM performance, while in the other cases, the performance, the throughput is lower and lower. So we have some conclusions. The first conclusion is NUMA awareness matters a lot. So the NUMA lookup PMem accesses may increase the performance, and in our case, can increase the throughput by a lot. And the bigger the enter size and the load, and the impact of this is more significant. The other conclusion is persistent memory is a good fit for certain distributed use cases like distributed caching. Even though persistent memory has a performance overhead compared to DRAM, the networking related tasks like serialization, non-copying between buffers, or inter-thread communication can compensate for the performance overhead of persistent memory. So it turned out the traditional caching use case is a good use case, and it works really well with persistent memory. There are other use cases that we identified as still have the performance overhead compared to DRAM, like full scanning the entire data set, which comes with many read operations that touch the persistent memory. It can still slower, but the good thing is the traditional caching can benefit from persistent memory. So as a summary, we've shown that persistent memory can be in performance parity with DRAM in a distributed environment. We also shown how easy it is to integrate with Memkind, and how Hazelcast brings the persistent memory into the JVM ecosystem. If you are interested in more details, then there is a blog post on the PMem.io blog and the Hazelcast blog. If you want to give Hazelcast and persistent memory a try, you can consult the Hazelcast manual, and you can learn how to configure the persistent memory with Hazelcast. And thank you for the attention, and now we are ready to answer your questions if you have any.